Hi there, Justin from Empower Operations here, and today we're going to be exploring constraints in OASIS through the ANSYS integration. Let's look at a real use case scenario for OASIS. Imagine we are engineers tasked with finding the best possible design to minimize the volume of a part while being tolerant of a certain level of stress. First, we need a way to take inputs and simulate these outputs. To do so, we've created a model of an orthogrid, a structure of rectangular openings in a piece of metal with a thin backing plate. We will use it to gather information on volume and analyze structural integrity with ANSYS static structural and buckling. Along with its one objective, the model has 27 input variables and 2 constraints. Constraints are additional design criteria put on your model. These could be physical constraints, like there must be a backing plate on each hole. For the simulation to be worth running at all, constraints like this have to be satisfied. You could also have a constraint describing acceptable results, like the structure must be able to tolerate a certain level of stress. The objective of our optimization is to find the minimum volume of the orthogrid while satisfying these constraints. Designs that fail constraints are referred to as infeasible and will be represented in OASIS with light blue. Now that we've got a better idea of what a constraint is, let's get back to setting up the model. 25 of the 27 inputs represent the size of the squares. The other 2 represent pocket depth and plate thickness. Outputs are model volume and load multiplier from the buckling analysis. I briefly mentioned earlier that one of the design criteria is that the pocket depth should not create holes in the model. To satisfy this, we place an inequality constraint to limit the pocket depth to less than the thickness of the plate. Another important requirement is to ensure OASIS proposed designs meet structural stiffness criteria. Let's add another constraint on the load multiplier. The OASIS optimization kernel's intelligent sampling strategy will direct sampling towards designs that satisfy constraints rather than relying on random sampling. This will save a lot of time because the stress constraint is dependent on the buckling simulation results, so reducing the number of designs that fail it will minimize the time spent simulating infeasible designs. And now you're ready to start optimizing. I hope this video will allow you to better use constraints to find an even faster way to your best design.